In last section, we discussed about operational amplifier OPAMP, and what we studied basic block diagram of OPAMP, what are the different parameters of OPAMP, and OPAMP with a different type of load like resistive load, diode connected load, current source load, and the most important one was current mirror load. Okay, and in this session we will discuss about the cascaded configuration, folded cascaded configuration of OPAMP. Okay, or the cascaded configuration and folded cascaded OPAMP. The cascaded configuration of OPAMP is same as single stage cascaded configuration is same as that we discussed in our differential amplifier. The folded cascaded we didn't discussed in our differential amplifier, but that concept was also applicable for normal differential amplifiers. So single stage op-amp is nothing but a differential amplifier itself. All the properties are same. Here the most important one is single-ended operation of not here it is single-ended operation of differential pair or the op-amp with the help of current mirror circuit. The derivation is very important, and usually for university exam they will ask this derivation. Okay, there also we need to find the effective transconductance and effective output impedance, then we can find the effective gain. And now we will start with the cascoded configuration of op-amp or telescopic cascoded op-amp. So telescopic means the elements are stacked one by one, and to get the more gain we can cascade more stages. Okay, the working and the analysis of this cascoded configuration is same. As per the structure, what we need to notice is the upper half we are using PMOS device, and lower half we are using PMOS device, lower half we are using NMOS device. And the second one we need to note is that the number of elements in the upper half must be equal to lower half to equalize the resistance in the upper half and the lower half. Otherwise we will not get effective output impedance, a proper output impedance of this circuit. And for this differential amplifier, and the extra cascaded configuration all are in saturation mode by external bias. Here it is VB1, VB2 and VB3. We are not discussing about the value of VB1, VB2 and VB3. Just we are evaluating the effective transconductance of this structure and the output impedance of the structure. So to evaluate the effective output impedance, here the inputs for finding the effective transconductance, what we will do, we will short the output to ground and we will evaluate the current through the circuit I out, and we find the transconductance GM equal to I out by V in. The procedure is same as that we discussed in the previous lecture, like current mirror configuration. So from that we will get the GM value is nothing but it is equal to, here also it is minus GM1 or GM2, or it is equal to minus GN. For the simplifying the analysis, we are assuming that all the MOSFETs are identical in terms of NMOS. All the NMOS are identical, transconductance and output resistance are identical, and upper half also all the MOSFETs are identical. And second, we need to evaluate its output impedance. So output impedance evaluation of cascaded configuration also we discussed earlier. Here just we'll brief that one. To evaluate the output impedance of this structure, so in cascaded configuration we don't want to use usual method. We can apply the basic idea from the normal cascaded structure. Okay, normal cascaded, so common source cascaded configuration itself. So from that we can evaluate the output impedance of this one. We are not deriving using applying a voltage source and finding the current. We are not following that usual procedure because that took long time, as we discussed in the previous session. like in current mirror circuit. This will become more complicated. So for avoiding that, what we are doing, just we are splitting this resistor, the R out, from here into two paths. That lower path we denote it as Rn, upper path it is Rp, and then we will evaluate the value of Rn and Rp with respect to this output terminal. So if we consider Rn, lower path, this M4 is cascoded by M2, and this M2, for evaluating resistance we need to ground all the inputs, and this is also a virtual ground. Okay, so the value of VGS is 0 here. Due to that there is no input signal. This we can simply replace with its internal resistance value R0. Here it is N, so R0N. So this one is simply, it's become a MOSFET with some bias VB with the degenerative resistance R0N. Then the output at this point is nothing but the Rn. We can write it as Rn is the reflected resistance by this one, that is the gain of the intrinsic gain of this one, that is GMN into R0N, 1 plus GMN into R0N into the reflected resistor of R0N, and the plus resistance of this device, that is again R0N. If you are giving numbering, this become GM2, R0N2, here it is R0N1, here is R0 or RON2. Okay, so this will be the effective resistance that we are seeing here. And if you are looking from this one, here M2 or M6 is cascoded using M8. Here the resistance become, in terms of this device we can write Rp as 1 plus GM6, its intrinsic gain is R0P of 6 into the reflected resistance R08 of R0P of 8. Okay, R0P of 8 plus R0P of 6 will be there. So these two resistances are parallel, and we will get an effective resistance. And finally we will convert this one. We can neglect the value of 1, and as this R0 value is very small compared to GM6 into R0 square, so it is GMP. Here it is GMP6. GMP 6 into R06, R08, and this one become GMN 2 into R02, R02 and R04. Okay, my mistake it is. With respect to this one, it is GM4, R04, R02. Here it is GM4. Okay, here also GM4. I thought it is G1 and 2 here. Okay, that's fine. R04 and R02. GM4, R04, R02. Or we can approximate, if all are identical, we will get GMP into R0P. Here also P is required, R0P square. Here it is GMN into R0N square. So that will be the effective output resistance, parallel combination of this one, and the effective output resistance R out become, here I will write R out become GMP R0P square parallel to GMN R0N the whole square. It's a huge value resistor that will improve our gain. We can get a cascoded configuration. If we add one more stage, it become GMP into R0P whole cube and GMN parallel to GMN R0N whole cube, or R raised to cube will be there. So the resistance will increase and the gain will increase. But in textbook, in the analysis, they also consider its body effect, because this M4 and M6 are not grounded in this analysis. because here in this source this device is connected, in this source M4 source M2 is connected, so they consider body effect also. In final stage they will neglect this body effect, so instead of along with the GM2 they will add GMB also, body effect also. In the final stage they will neglect all these things and write the equation similar to the square time itself. Okay. And the major drawback of the cascaded configuration is that output swing is limited. That also we discussed in the previous lecture. So output swing is that to keep all the MOSFETs are in saturation condition. So here I am removing here. To keep all the MOSFETs in saturation condition, we need to always follow the such conditions such that VD set or VD must greater than, VDS must greater than VGS minus VTH. So if we have an overdriven voltage for these two, then the minimum value of output V out minima is equal to the overdriven voltage of these two, VO4 plus VO2, because it must keep a minimum voltage which is equal to overdriven voltage of these two. Overdriven voltage is nothing but VGS minus VTH. And in practical devices, this ISS is also implemented using MOSFET, then that overdriven voltage also will be there due to overdriven voltage due to ISS also there. And the maximum value, what is the maximum value of this one? To evaluate the maximum value, we need to reduce something from VDD. With respect to PMOS, also it also need to satisfy this condition. So value of B max is limited by the VDD, this VDD minus overdriven voltage of these two devices, like VDD minus the overdriven voltage of VO of 8 VO8 plus VO6. So if we cascade more number of stages, more number of MOSFETs upward, or more number of stages are cascoded to this one, the number of overdriven voltage required increases. So the effective value of V minima increases and V maxima decreases, or the output swing decreases. To solve this one, we will use two ideas. One is folded cascode configuration, and second one is two-stage OPAMP. Okay, two-stage OPAMP is there. Here the actual derivation is there. Actual values are expressed. Actual values of the output swing are expressed here. Here there is a VGS 9 is given. This 9 indicating the ISS MOSFET. You can write it as overdriven voltage of ISS also. Everything is fine. Okay, here is fine. And upper side higherly is limited by 2 MOSFET. Here it is expressed in terms of order both side. We explain in terms of even side. Both are fine. And the total swing is twice the 1/2. So the total output swing is 2 into the swing that we observed. And please note that while writing the overdriven voltage of PMOS, make sure that you are using the modulus, because its overdriven voltage is negative. Okay, so make sure that it is modulus is used. So that is the basic working of cascoded configuration, telescopic cascoded configuration. And another one is there, telescopic OPAMP with a single-ended output. For getting single-ended output, we need to use current mirror. So just observe that we are making the current mirror configuration in both the cascoded stages, and here also the derivation will be the same and gain will be the same, overdriven voltages will be the same, but here we will get same gain in single stage using current mirror load. mirror load. Okay, current mirror load. And I think in textbook also they didn't give any derivation. You can directly write the formula. It's enough, I think. And next one is, what's the drawback of this telescopic cascoded configuration? The one main drawback of this telescopic cascaded OPAMP is that we can't create a buffer or voltage follower. In voltage follower, what we need, if we consider the voltage follower structure, here it is, Vin is there, minus, we will connect like this one, right? V0, V out become Vin due to the virtual short of our OPAMP. So for getting the voltage follower circuit or buffer circuit, we need to make sure that output is shorter to input. That configuration or the buffer configuration is not possible in telescopic cascaded OPAMP, because when we connected output to the input, if we connect like this, the output swing, we can connect, no issue, but the output swing is very low in this configuration.